Alright, so just to make sure you're seeing the slides, right?
Yeah.
Yeah, cool. So I got to get it shown again. Right, so I don't need all that. So the first topic is magnetic system. So the first thing you will need to know obviously is the basics of it, right? So what flux is? Well, we know flux is the total amount of the magnetic field passing through the given surface area. So I think I could draw up on this. So remember the flux is just like normal flux lines, right? It's just flux lines. And you basically have a surface. And if you could literally just count the amount of flux passing through a given surface area, that would basically just be the magnetic flux, right? So that's the first equation that you need to know. So flux is B by E. So instead of the other stuff. So we have magnetic flux density. So it's basically the flux divided by the area. So the flux is just the lines. When you divide the lines by the area it passing through, you get the density of it. Because that's what density is. You basically have an area and the concentration of stuff in the area is basically the density, right? And the unit for it is Tesla, right? So that's what B is. And we know A is a cross-sectional area. So basically, if you have a shape, a 3D shape, if you cut a 3D shape in half, you will get the cross-sectional area, which is just the area of the inside area, right? So it's either side by side, pi r squared, and that is it, because either going to be a circular cross-sectional area or it's going to be a square or a rectangle, a cross-section area, right? Either way, side by side or pi r square, nothing else. Because I never see a question where they give a triangular cross-sectional area and all that. So them things they don't really matter, right? And the last one is the magnetic field intensity, right? So the magnetic field intensity is the magnetizing force that produces the field in the material. So when you have a bar, North Pole, South Pole, well, you have these lines that go around. And if you could just zoom in on one piece, the intensity of that magnetic flux there, or the strength of it, or the thickness of it, is basically what the intensity is basically how intense the magnetic field is. Alright, and yes, it depends on the current and the geometry of the material, because we have a equation F, sorry, I'm going, that's not yet, yeah, F is equal to HL, and we know F is Ni. So this should be familiar. So basically, if you change I, you'll basically be affecting the field intensity, right? So note you need to know what flux is, magnetic flux density, and field intensity, and yes, you need to know what the unit is. So unit for flux is Webers, B is Tesla, and H is ampere meter, right? This is basically a summary to remember the stuff, right? So any questions on this slide, or you're good?
Good.
Oh, cool.
Good.
Nice. Alright, so I think you all know the screw rule, right? Alright, so it's the right hand screw rule. So basically, the right hand screw rule gives you the direction of the magnetic field and a current carrying conductor, right? I think you all use this for one of the magnetic system question. So get the direction of the currents in the circuit itself. So anytime you have multiple coils, you basically have multiple currents. The currents going to either aid each other or oppose each other. So you just have to make sure and check. So if you have a coil and you have an input current, you just kind of follow it. So this gonna come around here, around. So you basically, if you use your right arm and your fingers will basically just point in the direction of the arrows. So in this case, if you use this, your thumb will be pointing down, based on the direction of the arrows, right? And that's your screw. And you basically use it to determine the direction of the field or the current, mostly the current. Yeah, because in some questions they will just give you two coils and you had to know if the currents go and aid or oppose each other. Yeah, so how, okay, I'm gonna show you what I mean by that. Right, so we have I1 here and we have I2 here, right? So anybody take a guess or you'll try it. So use your right hand rule and let me know which direction the flux or the current will pass through. Either go up for this one or down. Which direction you think it will go, up or down, based on your right hand screw.
I say up.
Up. What do you say you'll say?
Down?
Down? Alright, so I think I have one more person. Sorry, what do you think? Up or down?
He typed up in the chat.
Oh, I can't see the chat because share my pop. You can talk unless your background noisy. So yeah, okay, so you see, so yeah, right, if you follow the current, this gonna go this way. And it will come back around and it will go this way. And it will exit. So your fingers itself gonna curve from left to right to point in the direction of the arrows. So therefore the arrow will go up. Yeah, it won't go down because down implies that the arrows going this way. Because if you point your thumb down, the arrows go and point from right to left. But in this case, the arrows, aka your fingers, pointing from left, but curling from left to right. So it's pointing towards your right palm. So your thumb will be pointing up. Everybody seeing that? So that's
Yeah.
Yeah.
nice. Well, redemption time. So try it for this one. I2.
Will I go down this time?
Okay, you say down. So what you said? What you say? Up or down?
I say up.
Alright, cool. Alright, so pointing the thumbs, the fingers pointing from left to right. So yeah, it will be pointing up. Nice. But you'll notice in this case, these two fluxes will be opposing each other.
Yeah.
So when you're doing a calculation,
Even minus?
yeah, it will be a minus here. It will oppose each other, so it will be phi 1 minus phi 2, or whichever reference you're using. But most of the time, in these type of circuits where you just have one continuous part, what I mean by that is, I think you also saw the one where it have the circuit familiar. So you have the coil coming
Yeah.
in, and then you have a coil here. So basically, if this flux going through here, and this one coming up, and the center here will basically add together, right? Remember that? And then you'll basically have to use loop analysis because you'll technically have two currents flowing. Basically, like if you have a circuit and you have a resistor in the middle and at the ends, I forget a resistor. Okay. It's basically like loop analysis you do, but you're just making sure that you basically derive the equation. But most of the time, you have to get it in this form first because you have to get the reluctances. So you'll be dealing with a circuit either way, right? But that's basically an example of when you will use the screw. When you have different NIs or MMFs or different coils on the same pathway, you have to make sure that the aiding or opposing, because that will affect how you do the calculations.
Most of the question from past papers, when they give you two coils, is the same approach as this,
Yep.
other than the torus.
Yeah. So anytime you see two coils, just know you have to make sure and deal with them. It's basically like superposition you do, right? But there's just loop analysis. Okay, so everybody go to this one.
Just to recap, so it coming in and use your right hand, your screw rule, and that's how you know the direction of the current.
So the first thing you have to, the responding variable is your thumb. The manipulating variable is your fingers. Yeah. So I'll just use my index
Yeah.
finger and my middle finger and just like wrap and point that to the direction of the arrow. And my thumb does just make sense at the end. I do so I'll do my pinky and the ring finger.
So you follow the arrow with your fingers and your thumb
Correct.
go point the direction.
Think of the arrows as the tips of your fingers. So if you the tip of your finger going from left to right, and your thumb will be pointing up.
Yeah, I see what you're saying, thanks.
Yeah. So everybody good, right? Right.
Yeah.
Right, so this one, the field intensity creation. Sometimes in the exam, they could ask you to explain how the field intensity is created. So basically, what I did, like I did use chat and stuff, to just get a paragraph where we could go through the stuff piece by piece, right? So you just need to know the flow, the main flow. I think I explained all this over and over, right? When you have a current, the current does create a field intensity. And that field intensity does give way to a magnetic flux density, right? So when you have current flowing in a coil, the coil will produce a magnetic field. And the magnetic field will have a different flux lines, or a thickness of flux lines. Either the flux created gonna be real thick, or it might be sparse, real spaced out. And that will give you a density. Remember, density is the amount of flux passing in a unit area. Yeah. So if you read it, so take a read. Everybody take a read. Take a read. I feel like reading it. But you'll have access to it. So I'll give you like a 20 seconds to read. And ask questions if you'll have any about the paragraph.
I have a question, right?
Yeah, okay, man.
So ampere circuit, ampere law is only applicable for a closed loop,
Correct.
not if
Right.
it's a air gap
Correct.
or if it's different materials.
Correct. Yeah, well done. Which is what we had to go. We can go through that just, but yes, that's a good observation. As ampere
Okay,
circuit,
cool.
it have to be a closed loop. If it's an open loop, tough. Yeah. But it have ways to simplify it in order to use it. Yeah. So that is good.
Yeah.
Alright, cool. Right, paragraph makes sense?
Yeah.
Yeah, it does.
Cool. Yeah. I can't hear Kazari, so I will ask you to do it. Right. I don't want to go. Alright, so BH cube. You gotta remember what BH cube does, right? So in a BH cube, the two things you gotta remember is well, it relates B to H, right? So B will equal to mu H. So if they give you the value of B, you can get the value of H, right? And vice versa. The linear portion of the graph, if you remember, is B, y is equal to mx plus c, right? You gotta remember that from secondary school. So in this case, y is b. The m would be mu. Then we have h, which is x. And then plus c in this case is 0, right? Because it's starting from the origin. So the linear portion of the graph gives you the permeability of the medium itself. So if you run a question and you get a beige curve and it asks us to calculate the permeability of the medium, you just approximate the linear portion of the graph. So just kind of use a ruler and draw like a straight line up to where it's straightened, and then you just pick 2 points and you do your normal y2 minus y1 is equal to, well, y2 minus y1 and x2 minus x1, and you get a gradient. And that gradient is the permeability of the medium, right? So 2 questions. If mu is free space, would it be mu 0 or would it be mu r by mu c? Which one do you think it will be? So if I tell you the
It will
medium is A,
be mu c.
if it's A, free space, would it be
It will be
mu
mu 0.
r by mu c?
Be mu 0.
Yeah, because it's free space. So anytime this
It's
says
a
this will
ferromagnetic.
be the same. So if this is a non-ferromagnetic material, it will be mu 0. Because it's have relative to A is 1. Yeah? So you'll have 2 cases. So if it's a ferromagnetic material, okay, erase. Wait, I'm talking erase
So
this.
if it's wood, would it be just 1 also?
What is that? If is?
Wood, which is non-ferro, it'll be 1.
Well, what is a non-ferromagnetic material? So the relative permeability compared to mu 0 will be 1. So everything is relative to mu 0.
It's a question like that was in tutorial.
Yeah. So mu c is basically you have, sorry. I need to erase that piece. Actually, I don't need to do that. I could ask for it. I need to stress. So we know free space is mu 0. But what will be the equation for non-free space or ferromagnetic material? What you all think it will be? What will be the
For mu c, you're talking about?
yeah, so what will be the equation for mu c for a ferromagnetic
Mu,
material?
mu 0 by mu r relative permeability.
Permeability.
Relative permeability, right? So that I
Yeah.
agree with that?
Yeah.
Alright, cool. Alright, so that is 2 cases. So you have to read the question properly. Anytime we do an air gap question or like composite cores and all them things, you have to make sure that you're using the correct mu. Okay, if you do that, you get it wrong. A common mistake students just make is just calculate one mu. So the material might have an air gap, and they will just use mu 0 for everything. Even when they're doing the core material, they will just use mu 0, which is wrong. Because for the ferromagnetic material, you had to use mu 0 by mu r. So you had to read the question. Sometimes they would not give you a mu r, but you had to make sure that it says a non-ferromagnetic material. So if you don't get mu r, you can kind of assume. Because if when heat materials are not ferromagnetic, have no mu r. So just have to read the question properly and don't fall for the tricks. One
I
more
could
thing.
ask one
Yeah,
question to that.
what's going on?
It's a question where it was like steel and it just give
Steel.
you mu 0, but it didn't give you mu r or any
What?
curve, anything.
They give
You'd have
you
to.
what?
They just give you mu 0 and then they
Alright.
say it was a ferromagnetic material, but they give you no mu r. Could you assume then?
Now, well, if they say steel, they just say
Yeah.
steel alone,
Yeah,
and they
it was
didn't
a
give
old
you.
question.
Alright, cool. So if they just say steel, they must explicitly tell you cast steel, sheet steel, let's have different ones, right? If they just say
Yeah.
steel and they give you mu 0, the first question was to calculate the relative permeability.
No, I believe it was, I think it was to find B or something like that. I can't remember off the top of my head.
Cool, but I can send it someone I could missing some information. But one more thing, right?
Yeah.
Anybody could answer. So when you have the value of B, right? Does the value of B change through the air gap and through the core, or is it the same?
For B, well, it depends on the material. If it's
But
different
if I have a
materials, it could
closed
change.
loop, so let me say I have this. So we have an air gap here, and we have all this core material and have a coil here, right? So this whole material, based on the pathway, you will calculate a value for B, right? So you have B core and you have B air gap, right? So my question is, for this material, would the BC and the BAG be at different value, or would it always be the same value?
It
Crickets.
would change, I believe,
Nah.
I think it will be different.
because it's AN is a different material. But if it was one material, it would be the same.
Okay, cool. So, nice. So what's all wrong, right? So the
I think it's H that will change, not B.
correct is right. B
H.
always the same. For the material, once you calculate a value for density, it will be the same throughout the material, even through the air gap. It will be the same thing. So BC is always equal to BAG. And as I said, it's only the H will change. The intensity in the air will be higher. Yeah. Well, that'll be lower than the core material. But you will use that, or the use the B to calculate H. Because you will know what this is, not so? Because if it's A, you will know there's mu 0. And if it's a core, you will know it's mu 0 by mu r. So technically, if you have B, you can calculate the intensity for the core material and A. Yeah? So,
Would it
yeah.
change for a different material though?
Yeah, obviously we're changing for different material, because different material have a different relative permeability. So if you change
Like a
the,
minimum multiple.
if it's multiple, yes, it will
Yeah.
change, but the B will be the same through all of them. They all will have a different intensity, but they will all have the
Mm-hmm.
same density, which is B.
Flux.
Yeah?
Okay, cool.
So
Makes
remember,
sense.
B is equal to mu H. If this is the same, if like I said this is 2, right? If you change the material, you're changing this now, so? Because the material will have a
Oh
different
yes.
permeability. But when you change this, since this is the same, you'll be able to calculate the H due to this. Yeah, so the B will be the
Okay,
same.
makes sense.
As our
I
B
thought it would change.
won't be the same. So if them give you a global B, you could do real stuff with that. You don't have to do nothing separate. So you good there, right?
Yeah.
Nice. So good. And we continue. Nice, yeah. So somebody was talking about ampere circuits, all right? So the integral of the magnetic field around a closed path is equal to the current encircled by the path, which is basically what you're doing whole time, right? So you can apply it when you have high symmetry, which is exactly what you're doing. So is it either this way, or is some looking like this, right? I mean, if you cut it in half, the two cross-sectional areas and the ends will be different sizes. What I mean by that is, like, if you have a oblong looking circle, you notice how this material doesn't have high symmetry compared to this. So in this case, you will not be able to use it because the cross-sectional areas will be different. So therefore, if the cross-sectional area change, the flux will change, which defeats any whole purpose, right? Another place where you can't use this is like if you have a air gap. Yeah, draw that good way. Anyway, I cannot do that bad there, but okay, anyway, I ain't gonna change it. So when you have an air gap here, you notice it doesn't have a closed path, right? So when you don't have a closed path, you can't use the ampere circuit law directly, meaning just flat out. You have to make some changes in order to use it. Because how I remember this is in the equivalent circuit, if you have an air gap and core, it will be two separate resistances, right? And if it's just in series, from the time you have two separate ones, you will be able to use the equation one time. And the simple version of this is basically just Ni is equal to HL. Yeah? I think you all just should be familiar. But in the exam, yes, you need to, if you say state ampere circular law, you should be able to know the definition and this equation here with the integral. Cool. Right. Yeah. Well, I went through this already. So if the closed part is a circle, which is what we did just now, of radius r, so you basically have a circle, and you have a radius. Well, we know this already. And if you do the integral of it, you basically get h. This is L, remember the L for our circle is 2 pi r, right? So it'll be h, L, and G is just I. This is just I. It's current density. Yeah. So if you integrate the current density, you would get the current, right? And if you make h the subject of the formula, you end up with a nice equation for h. Yeah. So there's two. H is equal to I and 2 pi r. And if you only use the closed part, when you could use ampere circular law. So if you give you the current density, and you have the length, you could get the field intensity. Yeah. Which is basically just a derivation of this. Anyway, the next one, because remember we know B is equal to mu by h, so we're basically just replacing this. This is basically just h. So you're just placing this in the equation, you get equation for B. Just like normal. Oops. I'm not supposed to zoom in. Alright, so you all good there?
Yeah.
Nice, so you just
Would they
get,
ever give you a question like this though?
well, I don't know. I can't answer that question. All I do is,
I never really saw it before.
yeah, so it have multiple ways to, but there's not really the ampere circular law, you all been using it all this time. As I said, didn't know, probably didn't know yet that I was using it. I think we did a question where you had to use this to calculate B though.
Yeah, I remember that one, but not the other formula.
Yeah, you're beating up about which one to use to calculate B. Yeah, but cool. So that basically ampere circular law. Right, so which kind of went through this just now. I just take it from chat. When not to use it when you have no symmetry. I think I just went through that, right? So short wires and cold irregular shapes, right? Uneven geometry, right? Mixed materials. I think Vernon was talking about this, right? So anytime you have a mixture
Yes.
of materials, it wouldn't be one continuous circuit. It will be breaks. Yeah. And then, well, the magnetic field is not constant. Hold on. Correct. So the magnetic field must be constant because it's ampere circular. It's symmetry you're looking for, right? So, but most of the time, if you bring in a question, you will know what to do. Sometimes he might just ask you when you can't use ampere circular law, and the answer to that is when they have little or no symmetry in the material. And if he asks you examples of mixed materials or irregular shapes, are the two things I remember. Yeah, take it there. So, well, just to run through this quick, this equation. So force on a moving particle thing. I don't know if you all came across this. You all came across this before?
No.
Cool. So
No.
it's just an equation, right? I just play it just in case. So I just skip through this. This is important. Force on a conductor. You all should have come across this already. This equation here, which is the BIL sine theta. You should look familiar, right? So there's the force
Yeah.
on a
Yeah.
conductor. Yeah, so it's B, the density by the current, by L, by sine theta, which is the angle, right? So this is an important one. But in a final exam, you wouldn't bring anything that simple. You might have seen that in a midterm or something. Yeah. So there's nothing to steal. And the magnetic dipole moment, that's, that's giving you all the equations. So you all would know, right? And well, just same thing. I really care about that. Alright, so again to the fun stuff. So the induced EMF. So how to induce a EMF? So let me see. So a target in, right? So all we to do is I give you a magnet and I have a coil, right? So I want you to take a shot and explain to me how the EMF will be induced. And you could use any law that you want. So I'll give you like a 30 seconds to think and then take a shot.
A magnet and a coil.
Yeah, so I'll give you a magnet, a north and south pole, and I'll give you a coil.
Yeah.
And I'll wait to walk me through how the EMF is induced and what laws they use. So the two laws is very important. They use that all over the place.
Will it be sunny slides after?
Yeah, that's nice.
Cool.
Right, so just, whenever you're ready, you can start. I wouldn't stop you.
Okay. All right.
Mhm.
Okay, so I think we'd have to use ampere circuit law for one. And wait, let me explain why. Okay, so I said we have to induce, well, basically, we have to apply a current to the coil. And well, in that, the coil produces its, well, when a current is, well, if I'm on this spot here, just a minute.
Yeah, that's okay. That's okay. Nobody, I'm not gonna do it. Just think about it. So that's the edit way you're doing, right? Remember, all you have is a blank coil. It's have no current in the coil. It's just a coil. This is what you have. Again, yeah, this a coil, and the coil probably
So I
just
can
have
apply a current over it.
yeah, just have a galvanometer to tell you the direction of the currents. And again, you have a little magnet, north and south. That all again, you ain't getting no current source, no battery, nothing. That is all you have. I just want to induce a EMF in this coil. So can I use this magnet and this coil to induce a EMF?
You can place the magnet into the coil.
Okay, so you're right, and okay, go ahead, you're good. When you place the magnet in the coil, right, what gonna happen?
Right.
So okay, so I go through it. The first thing, right,
Yes.
is when you move the magnets, you remember what inertia is?
Yeah.
Yeah, so anything that, well, Faraday's, not Faraday's, Newton's third law of motion, it's first law
Newtons.
actually.
It's first
Anything,
law, first law.
yeah, anything in motion or stationary will stay like that unless acted upon by an unbalanced force, right? So right now, this coil, it's not doing nothing, right? And this magnet have a magnetic field on it, right? And it does go from north to south. Cool. So when you move this magnet towards the coil, and the coil gun want to resist the change that causing it. You want to resist it because obviously he wasn't doing anything before. So you want to stay like that, right? So this coil gun basically be, it will say, hold up, bro, hold up. And how can I repel a magnet? Remember, opposites and like charges for magnets. When you put a north pole next to a north pole, what it does do is repel or it does attract.
Repels.
Right. So cool. So we want this coil to generate a magnetic field in such a way that it will oppose this magnet here. Right? So obviously we know it will just produce something like this, right? There's a magnetic field. So my question to you is, would the arrow point from left to right or right to left to oppose? Which direction you think? This way, which one? Anybody could chip in.
Well, go point in the same direction of the magnetic field.
Which is it? This magnetic field So I want the arrow.
The magnet.
Yeah, so this moving towards here.
Yeah.
So this gun generates a magnetic field to stop this movement through it, right? So it wants to
Mhm.
oppose. So I need to know, just like how this have an arrow on top of it, I want to know the direction for the arrow on this induced magnetic field.
Left to right.
Okay, when you say left, why you say left to right? If you say left to right, if I bring something, look at the directions it will be going. It will be going in the same direction or a different direction.
It has to be going in the same direction.
Alright,
It's
so if
not
something
opposed.
going in the same direction, would it be opposing or aiding?
That'll be Aiden.
But NP wanted to oppose.
Opposite direction.
So in this case, it will be correct. It will go in the opposite direction. So when you move these together, you notice how when it close together, they will oppose each other because it's pushing away.
Mhm.
If it was going in the same direction, it will superimpose on each other and strengthen, which is not what we want to do, right? We want to
So like
oppose.
two south poles.
Yeah, we want to oppose because he was stationary and then he started to move. So if you start to move, I want to stay being stationary. So I will generate a magnetic field to oppose you, right? So now you have an induced EMF here. So now if you have a magnetic field, and you will have a current flowing in the coil, because the current is actually what giving you the magnetic field, right? So now we have this galvanometer at the bottom here. So we need to know what direction it will deflect to. We all think it will deflect to the left or to the right. Which one?
Um, to the left.
Okay, so when you say to the left, why is it to the left?
Because initially, before we do anything, was to the right. So if we
Initially it will
impose
be
a
zero.
change direction.
Initially it will
Oh,
be zero because it have no current flowing in the circuit, right? So
okay. I watching the image you have up.
yeah. Oh, it was tilted a little bit. Okay, cool. That's okay. But initially the galvanometer will be at zero. No deflection left or right.
It will be to the. It will follow the direction of the opposition, so it could be to the left also.
Okay, cool. So that way you say left or right.
This is the
West.
direction of the current, right?
Yep. That would produce that magnetic field in that particular direction. So,
It will be to the right. Then.
alright, yes, you are correct. It will be to the right. And I'm explain why it would be to the right. So if it going to the right, remember the current will be going this way, right? You see that going on? So if the current going in
I
this
know.
way,
See. I know.
it
See.
will go up so, and it will go this way, then this way, then this way, then this way, and then back down here. Right? So you're seeing when all these little magnetic fields aid and strengthen each other, the overall direction will be this way. Seeing it? So it will
Yeah.
strengthen a right to left direction. Okay. So this galvanometer will actually deflect this way. Okay. That makes sense?
Yeah.
So
Yeah.
now, so that is when it moving towards. So if you increase the speed at which you move the magnet towards the coil, the induced EMF will be higher or the deflection will be wider. Okay? Because it's like if you're doing something and somebody move fast towards you and you had to move real fast, you can't move slow. So inertia will basically strengthen. So if the coil move fast towards the coil, it will generate it will need to generate that EMF real fast in order to oppose. It's like an army. If you get attacked and you have to mobilize real quick, you can't mobilize slow. So the faster the incoming army coming at you, you have to mobilize faster than it to generate the defense. So it's the same thing here. If you move the coil faster towards the coil, if you move the magnet faster towards the coil, it will generate the magnetic field faster to oppose. So cool. So that is the first way. The second way now is when it's moving away from the magnet. So now instead of the magnet moving towards, it moving away. So if it moving away, what will change? Obviously, stuff will swap. But what will swap? What will swap? Anybody can take a hit. What will swap? So initially, when it's close, and right now, it have a magnetic field in the coil, yes or no? Have a magnetic field in the coil, right?
Yeah.
Right. So it moving, stop moving, right? So if I was to now pull the magnet away, which is basically pulling the thing away from the thing that was inducing, and I want in such a way to help it, because now I want to
Yeah.
aid. Because if I aid in, I will strengthen. Also, when I oppose in, I will push away. So now I actually want to bring him back. It's like, why are you leaving? Come back here. So you want to attract it, also. So if you're trying to attract it now, remember field lines. Right now, you have north here and you have south here, right? Remember, flux lines just go from north to south. So obviously it will oppose. So now what you want to do to attract it back is you want to put the north pole on this side and the south pole on this side also. So therefore the flux will go from, it will go this way now. And if it going this way
To be
now,
in direction.
correct, and that is it. It will just reverse the direction. And that is really all it is. And if you keep going back and forth, back and forth, back and forth, you end up with a sine wave, which is how AC, the current, is generated. Cool. So any questions on that? So that you good?
So this just to explain Faraday's law.
Yeah. So the first was Faraday's law. So when you're moving the coil, or you can move the coil or you can move the magnet. Once you have relative motion, you will have an induced EMF, right? Yeah, that's in relative motion. So anytime
Oh,
you,
I enjoy diagram to explain.
yeah, correct. So if a flux cut in a coil, it will induce an EMF. You all remember that from transformers, right? That basically what a transformer
Yeah.
do. And well, the flux, it can move the coil, it could change the size, all that it could do. And while Lenz's law, or Lenz law states that the direction of the induced EMF is to oppose the change that causes it, right? So Faraday inducing it, and Lenz telling the direction for it. So that's literally what we did here. So when you move the magnet, it induced the
Just
EMF.
repeat lenses.
Huh?
You can repeat lenses, Faraday's induces, and lenses
Right.
eat in it.
Lenz's law will basically tell you the direction of the induced EMF. So Faraday's law states that when you have flux cut in a conductor, it will induce a EMF. So Faraday just telling you a EMF will be generated, but it doesn't tell you the direction. So Lenz now come and say, well, okay, the direction of this induced EMF will be in such a way that it will oppose the change that causes it.
Thanks.
So that's Faraday's and Lenz working over. Alright, so let's have a note. So if the current flowing through the coil is increased by adjusting the source, the flux link in the coil will increase, and the EMF. So that's basically transformers. Okay? So transformers, all they really did is just remove the galvanometer with a source. So now you have this. Okay, now going into induction, so stuff. But I saw mutual induction does work. You basically have one coil with a magnetic field, and you put a AC voltage in the coil, so that will have a change in magnetic field. And when that change in magnetic field cut another coil, it would then induce a current. And I saw mutual induction as well. So this basically Lenz's law. So the direction of the induced EMF will oppose the increase of the coil current. Yeah, so I basically was going through that stuff. And this here is Faraday's. So lambda is flux linkage, right? So as the flux linkage changes, it will induce a EMF. Cool. Right, cool. So I think you'll know the equation for each, right? So when you have a circle or the windings itself, same equation you did from before. So it'll be H is equal to Ni and L. This equation looking familiar? It's the same equation for each. And that's basically Ampere circuits of the user. This is very important because how this would change, if it's a circle, we know the length, you just use R and you get 2 pi R, right? But how, and there's a question for anybody, right? If it was not circular, let me say it was rectangular, right? How would I now calculate the length. Because I can't use 2 pi r here because it's not a circle, right? But how I could calculate the length for this one? So this no longer here. So what will be this one? How we calculating that length?
Do we have any other nodes?
Where's that?
Like any other variable that given?
Did this. So like you said, they gave this as L1, L2, L3, and L4. Obviously, some of them I think give it, but I give it to you. So they gave this and the one L. How we can get L? So that I wanna give it a shot, so we will get that L here.
Yeah, I was gonna say you can add up all the different L's, right? Because that is the distance the flux passing through, right? Okay,
Correct.
so yeah, I'd say add up all the different L's.
Nice. I agree. I like what you say. You said L is the distance the flux passing through. That's a good way to remember it. Because once you remember that, no matter if they give you a circle, a rectangle, a square, a triangle, you will know that it's just the distance the flux passing through. Okay? Right. Question, so that since you say that, I'm gonna pick your brain, right? If I had an air gap in between that distance, that L, would it be the same L value or would I have to subtract the distance of the air gap?
So if you had a air gap in one of these things,
So like you're saying
I'd
this,
say subtract the air gap.
right? So you had to separate L core from L
L air
AG.
gap.
So when you
Yeah.
do the full thing, you end up with L. But L is equal to LC plus LEG, right?
LH.
So you just have to make sure and subtract it. Because it's two separate legs individually. But when you do the main calculation for the lengths, it would have be one total leg, right? The flux passing through air gap two ends. Okay, that's the distance.
Yeah.
Cool. Yeah,
Yeah.
so it's like you're playing a game and you're
We
passing.
just require more.
Correct. Well, when you say more, what do you mean by that?
Like reluctance and stuff, the calculation will be way bigger than the core.
Yeah, the reluctance gets correct. Anybody can tell me why the reluctance of the air will be higher than the reluctance of the core?
Is
Via
it
the,
because the permeability?
huh?
Is it because the permeability of air?
Right. I want you to give me the reason via the use of an equation. So that remember the equation for reluctance.
Yeah, me too.
So what will be?
It have multiple equations too. Which one you want?
So I want the main equation for reluctance, not any derived equations. So it only have one main equation for reluctance.
Okay, so R is equal to the length divided by the permeability of the material over the area.
Correct, that is the main equation, right? All the other R's are called derived equations, okay? So anytime you're calculating reluctance, this is the main one. Yes, you can obtain reluctance by the use of different equations, but this is the main one, okay? Right, so if I have this, how come the reluctance of the air higher than the reluctance of the core? What value in this make it so high?
Permeability.
Right, so in air, why will be higher?
Because you use the permeability of free space and not the permeability of the material, well, relative to the material.
Okay, so are you trying to say that this mu here gonna be a very small value for air?
Yeah.
Yeah.
So that's using math. So if this decrease by a lot, and this will increase by a lot. Yeah, so the mu for air is very small. And the mu for the core is not very big, but it's just big enough to not give you a huge value for R, right? So everybody cool with that, right? So yeah, so this slide basically showing you have H is equal to Ni on L, which is our very popular equation, and the main one that came from Ampere circuit law. Cool. Right. You all know this already, man. The magnetic circuit, you remember it? So you have F, which is the Ni, you have flux, which is like current, and you have reluctance, right? You remember this?
Yeah, the equivalent circuits.
Yeah, one thing though. Anybody could tell me the difference between resistance And reluctance?
Resistance is for the electric field one, and reluctance is for the magnetic field.
So that I can edit what you said there. You make a mistake in one of the pieces. But good one, I make a small mistake.
Okay, so reluctance is with respect to the magnetic field,
Mm-hmm.
and resistance is respect to the electric circuit, not
Correct.
electric field, electric circuit.
That's the
So
electric
V
field.
equals IR,
Nice. So
that
you have one.
equation.
So it's just the electric field. So you have no electric field, right? Yes. If you have something electric, it have a field. But based on this is the electric circuit or the electric component and the magnetic component, right? Remember, it's are two separate
Yeah.
circuits. Yeah. So remember, you have a voltage, and you basically have a coil, and then in the coil you have a core, and then when you have a current from the voltage, you will get a magnetic field, right? So everything up to here, the VI and the R is the electric circuit, right? And L also, because you have inductance in the coil. From the time you generate the flux, and the MMF is basically the strength of this here, you basically go across to the magnetic circuit, okay? So you have the electric circuit and the magnetic circuit. Everybody cool, alright? So sometimes I could ask you to
Yeah.
draw this. We know this one already. F is phi R, right? Not this R is not resistance, it's reluctance. A mistake a lot of people as makers that does use the reluctance R as the resistance that does give you any question. That wrong. Yeah? All R's is not resistant, right? They typically draw it differently for a reason because they know people will see the capital R and just run with it. So everybody cool here. So we know the next one, the electric circuit. So you have voltage or EMF, current, resistance, and you have inductance, right? Because the inductance will be part of the electric circuit. But you have this equation, V is R by I by L di dt, which is the change in flux with respect to the current. Yeah, so everybody get there?
Yeah.
You need to know how to draw those two. And I wanted to show you all here. I don't think I needed anything. But we knew this one already. F is Ni. I think that's all I wanted to show you. And then F is HL. Yeah, these equations looking familiar. So you have F is HL and you have F is Ni, right? Very important. Cool. Well, I'm you went through this already. You all correctly told me the equation for the reluctance. So this is basically going to the proof. I don't think so. Well, you can tell me. So went through proofs and stuff.
I don't believe so.
Right. So if
Keep
you
going through the equation.
right, cool. So the first equation is F is phi R, and the other one for reluctance is Ln mu, right? Yes, you should know the equation for it. So you all good there, right? Well,
Yeah.
I think I'll write for these the governing equations. So the first governing equation is F is equal to Ni, and this one F is equal to HL. So I'm going to spend a little bit of time on this, because you need to understand it, right? The F is Ni part, this is the simplest one, because this just giving you MMF. This simple, because there's just any coil parts. From the time you have I and N, you could get MMF. This is okay. This one now have more of the magnetic part of the circuit in it. Because this L, as I said, is the flux part, the distance, and this H is basically the intensity of the material, right? So I'll go and give each of you all one scenario, right? And I'll give you all 1 minute, and I want you all to try to explain it in a way that hopefully we could understand, right? So alright, S, so there's your circuit. So M1 means material, right? So you have this material here. So it's made up of 3 separate materials, and you have your length. So you have your lengths of each. So they get a real length. So in this question, they give you different materials that make up the core, and you have the lengths of all of them, right? So that I said alone. So what I want you to tell me is which one will be the easiest one to use. F is equal to Ni and F is equal to HL. Based on the one you pick, I'll wait to explain to them how you will implement it. So yes, you have a little coil coming through. Cool. And Vernon is yours. Well, I think Kazari can hear me, so you just have to listen. So take a minute, look through. So the first thing I want is which equation you're using. This one or this one. And the second thing is how. How would you do it? How? How? Obviously both of them we calculated that, right? But how? How? How would it change depending on the materials you have? So take a
So we
minute.
just give on the
You get how
we
the
give on
circuit work.
M1.
You just had the circuit. M1 and M2 is different materials. So cast
Okay,
steel,
cool.
sheet steels, well, it does have different materials. But different materials in the same make up the core. Yeah. So I'll be back. Alright. Anybody wanna give it a shot?
Yeah, I'll take a go at it.
Alright, cool. So you have three materials, one core. Where's your thought process?
Okay, so I would use F equals to HL.
Okay.
We have three different materials.
Alright.
So that means we most likely have three different lengths. And if it's different materials, that means the permeability of each material will be different. So therefore, H will be different.
For each of them?
So, yeah.
Okay, I'll listen.
So I'm thinking, well, each will have like a different force, no? Because if each H is different and each L is different, you find the F of each material and then you add them together.
He was going so good. I don't want to get the answer. He was going real good, right? Everything up to the part where
Okay.
you tell me each different. If each different, we know the L's will be different, right? Based on the distances there. Okay, if you
Yeah.
see the main pathway, he gonna be this. He gonna be all this up to here and then this. So they have different
Mm-hmm.
length, right? So you call this one length 2, length 3, and length 1, right? So
Yeah.
that I current there, right? That I is from the magnetic circuit or from the electric circuit?
You gave me an eye. I didn't even see that.
No, well, no, think about it. So the two equations are called governing equations, right? But F,
Yeah.
remember F is Ni, right? That is the MMF.
Mm-hmm.
The MMF comes mainly from the electric circuit, right? Which is the
Yeah.
number of turns by the current, right? So my question to you is, I agree with the HL, correct equation, right? But the I
Mm-hmm.
part, okay, it said something that way to see why it's wrong, right? The I, that I coming from the electric part or the magnetic part?
The electric part.
Right. The I now, the I that's coming from the voltage connected to the circuit. That that voltage, you could change that voltage. You can't change that voltage, right? So that constant. Okay?
Yeah.
So your voltage into the coil constant, and if the voltage into the coil constant, and the coil constant, and the current will be constant,
Yeah.
so therefore,
Or she can use both of them.
follow me here. So we have the HLs, the HL part of way to split up for me. So you tell me they will have different Fs. I do agree with that part. It will have, it's not a matter of different Fs, but it will have sub Fs that add up to the main F. Because you have a circuit.
Okay.
So if you join the
They
equivalent
go
circuit,
have. Mm-hmm.
you know, join the equivalent circuit for that, the magnetic circuit for it.
Well, they go have different Fs.
You're correct, but when you say
Well, not
different,
different Fs, but sub Fs. What that what I
right,
mean? The different Fs I mean in sub F. So you go have like a F for M1, M2, and
right,
M3,
so get my
and then you'll
equation
have
right
a
here.
F total.
Right, so get my equation. So Ft will equal to,
FM1 plus FM2 plus FM3.
okay, I'll take that one, Fm1 plus Fm2 plus Fm3. Right, and if I
So it
continue,
will
what
be H
Fm1 will be in terms of HL?
HM1
Um,
HML
with H1
yeah
H1L1 plus
H2L2
plus
H3L3.
nice. This whole thing here will basically equal to N by I, because F is Ni. So this total
Mm-hmm.
MMF you have here comes from the number of turns multiplied by the current connected to it. Not so? So if they wanted you to
Yeah.
calculate the current, or the question say calculate the current, you gotta do separately, then divided by the number of turns, and you'll get I, right? If they
Yeah.
wanted F, you'll just leave it as F, okay? And always draw the equivalent circuit first. So that'll be F, and you'll have three of them in series, right? One,
Mm-hmm.
two, three, right? If somebody asks a question in the chat, I can't see the chat.
I think we're not just release this one.
Oh, yeah, go ahead.
I have a question, right?
Yeah, go ahead.
So the reason why you're saying you can solve it both ways basically, right, is because of how it's a closed circuit and the symmetry is same don't matter the way which formula you use.
Well, so, yes, but the trick in the question was to only have one. So F is Ni and F is HL. F is Ni, or F is equal to HL. So the Ni part comes from the electric. So this one here, most of the time, is just the Ni part. You just have to pull out from it. But this one now, I'll say that breakdown for us. You have to split this. The reason why you have to split is because it have different materials with different permeabilities, right? And different lengths. So anytime you meet a question like that, you have to do it separately. Make sense? You have to. If it's
Yeah.
just one material straight around, you have one permeability, one L, so you can get F one time. Cool. So this equation here is what has linked the magnetic part to the electric part. Right, basically, just link them together. Because if you have F, you could go across into the magnetic part. So that's like the magnetic part. And go ahead. But the the big one, Ni equal to HL. The other governing equation for on this side now is F is equal to phi R, which is R is the reluctance, right? You remember that? F is HL, F
Yeah.
is phi R, and then F is Ni. Those three equations is basically the backbone and majority of the magnetic system questions. Yeah. If you're doing this one here, obviously, based on what Cell did, you will have to calculate different R's, right? So cool. Well, Vernon, take a shot at it. Well, unless you understood what she did. You think yours would be different from what she did?
Well, I just have one less different type of median,
Well
which is
done.
I have 2 instead of 3.
Correctly
So
right.
we just take the same approach.
Correctly right.
So
Nice.
if it was just 1, we just go with NI then.
Well, if it's 1, it'd be H1L1 or just HL.
Yeah.
Yeah. N and I have no values from the magnetic path. So you won't be able to do anything with F is equal to Ni.
Oh,
Yeah.
I keep thinking like when I see the coil, they will give you the number of terms one
Yeah,
time.
they'll give it N, they'll get I, but all that is electric stuff. There's an electric path.
Right, the only
It won't
magnetic.
be magnetic. So the two magnetic pieces will be F is HL or F is phi r. Yeah. So
Yeah.
next question I'll give I'll give you it, right? So basically we know actually so that since you had asked me, right? The magnetic flux density passing through these three materials, would it be the same or would it be different? So the density for each
As in F.
yeah, the density passing through M1, M2, and M3, different or the same?
But each one of them go have different areas, right?
Okay, like we assume it's symmetrical, I mean all the cross-sectional areas are the same. But good. But in
Okay.
this case, all of the areas are the same.
Right.
So
But there's still different materials. So you're looking for the flux density, right?
yeah. So the question is, would the density be different going through each, or would it be the same?
I think it's. Hold on. It should be the same.
It will be the same. Say it confidently with your chest. The
It will be the
density
same.
through the core parts is the same. Whether they're going through an air gap, whether they're going through Jesus Christ, whether they're going through the core material, is the same thing. So no matter where in the loop you are, it'll be the same value. Yeah? Okay, if I ask you to calculate the H for each of them, you need B. Because it will be B is equal to mu1 H1, B is equal to mu2 H2, and you go down the road. Yeah? Cool. So, Vernon, piggybacking from what she said, if we
Yeah.
know the density is the same, so we know B is the same, right? We have this
Yeah.
equation here, this flux. This flux
You
here,
can
right?
ask if it's change, if it's different.
Right. So if B is the same, so you know phi is equal to BA. So we know this constant
Mm-hmm.
through the material. So if this constant through the material, you think this will be constant? If
Yeah. So it could be back to the analogy as said with the water passing through the pipe. You can have
yeah,
different pipe but the same water.
mm-hmm. Correct. So it will be the same because we know B will be equal to the
Mm-hmm.
flux over the area, right? So the flux will be the same. Cool. So the flux
Yeah.
is the
I
same.
have a question.
Go ahead. Mm-hmm.
So if the area change,
Mm-hmm.
would B change?
That is basically the next question I'm going to ask. So
Oh,
if the flux was the same, obviously you have different reluctances. Yeah. So you have different reluctances, right? But we know the flux will be the same. So you basically have to factorize the flux and you calculate the reluctances. Cool. But now, if you have different cross-sectional areas, you will have to do what Siddell did here. So it will be F is equal to phi 1 R1 plus phi 2 R2. That makes sense? Okay, we have to split it up into
yeah.
sub-Fs. Yeah. So when that will happen, when you have
And then you
different
get
cross-sectional areas.
FT.
Correct. But the B will still be the same.
So
Even if the A change, the B is the same. The flux could change, the A could change, but the density through the material will be the same. And it could go anywhere with that. Alright, so far,
yeah,
I
makes
went through a
sense.
lot of things here. Just fail to see it. So you could have a question with different core materials, you just split it up into sub-Fs. Yeah, based on what they give you, the biggest advice I could give you, if you look at a question and lace it with lengths, guess which one you're using, phi r or HL?
HL.
That'll be the easier one to use it because they give you real lengths. Anytime they give values with like B and thing, like they give you a global B, you could just use phi r. Because if you have the global B and you could just get everything else, right? But either way, no both. Cool. So I'll come back. So take a 1 minute break.
That was like
Go ahead.
the question we did
Mm-hmm.
in 2025 with the clamp, and it was
Correct.
like they didn't give him enough length, so HL was not applicable.
Yeah. From the time I look at that question and them and lace me with links, I automatically know it's fire. I use it. Get on nothing else to use. Anyway, I'll
Makes
come.
sense.
Alright, cool. All good. So I think
Yeah.
right. So this is basically what I was trying to tell you about, right? So take a look at this and let me know, based on the information you have there, which one you will use, HL or fire.
Well, they give you multiple materials.
Alright. Mm-hmm.
Yeah, but they get real lengths too.
Yep.
Well, yeah. So the gear lengths, the gear H's, and the gear A's and B's. So the cross section changing. So the A will change. So the flux will change to compensate for the fact that B had to be the same. That makes sense?
So
Because
these
if B is the
yeah,
same,
these
if one
are
change, the other
Yeah.
one will compensate, right? So yeah, so in this
Hmm.
case, if you look, you have Ni, and you see at the bottom there, the gear N. So most likely in this question, they wanted to calculate I. But how much materials you're seeing?
Cast iron and cast steel too.
Right, two, right? And they give you the cross-sectional areas, which are different. So you had to split it up. Anytime some
Yeah,
change,
the final total.
correct. So you have your equation here. So who wanna write the full equation for this circuit here?
Like the subcategory for H and L's.
Well, in this case they use R, so you had to calculate the R's. But H, to use H, what do I need to give you?
Mu and B.
Mm, well, yeah, they need something with B. So in this case, R, but to get the reluctance, you still need the lengths. But
Oh,
if
you
you
can use on the right formula, I guess.
yeah, you could use the fire. Yeah,
Yeah.
so cool.
And you can make the other one subject I formula.
Mm-hmm. So you use,
Ni is equal to phi 1 R I
but if it's in
plus
series, mm-hmm.
plus
Take a look.
phi SRS.
So if it's in series, when the flux be the same,
Oh yeah, yes it would.
mm-hmm.
Same flux, different reluctance.
Correct is right. Nice. So yeah, well that's basically it. So any questions on that?
No. So if it was in parallel, I'd be different flux.
Well, if it's in parallel, the fluxes will be same, but the total reluctance will be different. Come on, but
It'd
it's
be over two.
parallel.
No,
So
use
it's
the
about two.
parallel thing.
Yeah, so you had to still get you still gonna reduce it to one reluctance,
Yeah.
because if it's in parallel, you'll have to do the product over sum, and that
Yeah.
one total reluctance, so you're still gonna end up with a series circuit. Okay, you gotta get the
Yeah.
total flux. So either way,
In later questions had them like that.
yeah, so that
I
is
think it was
basically
mainly in parallel.
correct. So anytime you like dealing with it, or think of the circuit itself. Cool.
Hello.
Yeah.
Tazari requested if you could go through if you could go back over the composite course he got disconnected,
Oh well,
please.
because that time I might want to do that because I have a lot of stuff I wanted to go through. But I record in the class too. If anything, tomorrow when we start to do the questions, we could go through it. Yeah. But I don't want to go back because I like a couple more things I wanted to go through. Yeah. So cool. Well, that's basically a summary of what we just did, right? So basically the same thing. So you have phi r, fi, so hi li, and then you have hs ls, and you add them two together, and well, same thing for the reluctances. Yeah, with equations. Right. So well, some
Let's go back for 1 second.
Well, yeah, no problem.
Right. So if it was parallel, it's just the product over some rule, and you would get the same thing parity.
Yeah,
Right,
correct.
cool.
Because it's in parallel. Right, some extra equations. You have the inductance equation, which is lambda and I. Remember, lambda is flux linkage, right? And then you have so you have two actual equations. You have this one here, which is I think is not L, sorry, lambda n square
Equals to
I.
Li.
Yeah, and reluctance,
I
not
guess, yeah.
resistance, reluctance. Alright, a lot of people has mixed this one up. And then, well, we know resistivity is phi L, that's 13 there just in case. And we know L is n square and R, which is reluctance, right? So be careful. One thing that mix up a lot of students is reluctance and resistance. Because they memorize, yes, n squared and R. But because I say an n squared and R so much, then I've already paused to make sure, is it R as reluctance R or is it R as resistance R? And they just get bottleneck in the exam. So you make sure you know which R. I will say n squared and reluctance instead of getting the R in your head too much.
That was like W, capital WM and common WM.
Yeah.
Ng per volume and Ng overall.
Yep. That's the next one too. So how you see it is how you can basically remember. But anyway, so the next one is the scalar electric and your magnetic circuit. I have to skip all this and you get this. So in this, if you say to draw the unified circuit, which is basically made up of the scalar electric and the vector magnetic circuit, this is basically what we asked you for. So I'm zooming. So you will have to calculate, you will have F or V, so you have V from before, because there's an electric circuit. So you got V. I want my pen. Please give me my pen. Alright, so you have V, you have R, and you have L. So that's the components that make up the electric circuit. V, R, L, and I is the current, right? When you go across to the next side, you don't need to write all this. All this here you don't need to write. Cool? So that is scalar part. The vector part is basically just two arrows, and you have IA going in one direction, and IA going basically in one direction, because it's a vector. So the arrow going this way, and when I go back, it going that way. So you just memorize how does it look. So it's literally just two lines, IA, and the IA going in the same direction, but the arrows on the line going in the normal direction for the circuit. Then, why they call it a vector magnetic, because you have a CT, which is a current transformer. It's just a coil, or you can be drawing a coil, and 1 to any, which is a transformer in a way. And then you go across into the magnetic circuit, which is just Ni, which is the MMF. Remember, the MMF comes from a coil. So they're kind of modeling it here. Then you have the flux and the reluctance. So it's basically V, a battery, AC, resistance, the inductance, LA and RA. Then you have the arrow, IA, the vector. If you want, you could draw this if you want to. And then you have a CT. Then you have Ni, flux, and R. And you call that the unified electric circuit, or the unified circuit. And just a summary of some of the equations we went through before. So we have flux is BA. We have density is phi, which is mu, sorry, by H. Then we have this one, H and I. This is Ampere circuital law. And then we have the flux linkage is N by flux. And the last one is the inductance is lambda on I. And what's the next one? Anybody remember what the next one was? With the N square?
For
N
L.
squared I on reluctance. For L or
L.
For
for
L
lambda?
or for lambda?
L. This one.
N
For
square
L
over
is
R.
N squared on R on reluctance.
Alright.
I thought you
And
wanted for
for the
lambda.
lambda, no, which one it was?
N
N
square
squared
I
I on
over
reluctance.
reluctance.
Alright, cool. Makes sense really cool, yeah. Cool. So everybody
Yeah,
get there, right?
that was a derive
Yes,
because I
that's a
think
derive.
lambda is equals to
Mm-hmm.
Li or something like that.
Mm-hmm. So that's a derived equation that you're using there. Oh, cool. And that's unified circuits. Any questions on it? So you just need to
Nope.
really remember the parts of it. All I remember it is just you have this. So I R and L. So that part one and we had the I, right? So that's the first piece. So I know R, I know L, and I know V. V, right? Done. The next piece, so this should draw like a dotted line. I, a dotted line, I. Remember, it's just a vector, right? And then, well, the R will be going this way. I'm going to come back down that way. And like that piece. Done. Then on this part, you draw a line to separate. Then you just draw a CT, which is just a coil. And from the coil will basically give you the number of turns by the current, which is your MMF. Then you go through R. It only have one thing for your magnetic circuit, which is reluctance. And that is it, and here your flux. So I kind of like split it up into sections. Section 1, Section 2, and then Section 3 to make it easier for me to remember. So like good there, right?
Yeah.
So, well, run through this already, the BH curve. So the energy in a magnetic field, which is basically just the area bounded by the graph, right? So down here, well, the derivation for this is just to give you all the equations, right? But I will do think, okay, so what I want to show you here, right? The BH curve for non-ferromantic material is a straight line. It'll be a straight line. You don't have any curves and stuff for non-ferromantic materials, just a straight line. And the gradient of the straight line will give you the permeability of free space. Cool. That's basically what I wanted to show you here. And well, the only thing I remember here is that the area bounded is basically the energy stored. Okay, so you don't really need to all this. This is where you need to. So the energy, this is the Wm, capital one. That's the energy delivered to the magnetic field, rho. That's energy, as Vernon was saying, right? A is the cross-sectional area. We know what L is. B is your density, and well, you know what mu zero is. So this will give you joules, right? This is just energy delivered. That's the energy in a magnetic field, right? The other one is called the energy delivered per unit volume, which is common Wm. All you're doing is just removing the Al part. Now when you remove that, you'll basically, because really actually it would be Wm on Al on this side, which is where they get the energy per unit volume, which will just be B on 2 mu 0. So don't mix it up. Right? Any questions on that one?
No, it have two more formulas, two you could add on here.
Which ones?
Um, for total energy, it was a half Li square,
Oh yeah.
and then per
As
unit
you're talking
volume was
about
a
that,
half
yeah. Well,
is a half BH for per volume
mm-hmm.
for the bottom here.
Yeah, no long. That's a real derived equation. But yeah, yeah, correct. Well done. So that's another one you could remember. But just know one is a capital M and one is a common M, right? So cool. Right, this was going through how they basically got it. So all it did is just integrate between the B. And once you integrate, you just end up with a half B0 and mu0, which is basically how they get the equation. Right? Cool. And this one kind of self-explanatory. We went through this already. Right, so hysteresis. So this is important, right? Hysteresis or hysteresis, however you wanna call it, is where the magnetic flux density B, it doesn't depend or doesn't immediately follow changes. So what I mean by that, right? You gotta remember to have dipoles in the material, which is like little domains. So
Yeah.
we could draw, let's see how much we could draw here. So you have this arrow pointing this way, points in all the
Just for the
points.
BH curve.
Yeah, that's where the BH curve does come from. But it will be the BH curve for ferromagnetic material. Remember,
Yes,
the BH curve for non-ferromagnetic material is a straight line.
straight line.
Yeah, cool. So you have this core. So basically, when you experience or put this core in a magnetic field, the dipoles will try to align in the direction of this magnetic field, right? But sadly, that change doesn't happen instantaneously. It doesn't happen one time. So it will take a period of time for it to happen, which is where they got the this whole BH thing from. Yeah, we will go through that also. But just know the history of the artifact definition is basically a phenomenon in magnetic materials where the magnetic flux density B, it does not immediately follow changes in the intensity H, but instead it depends on the material's past magnetization history. So it basically means that initially, right here, some arrows like these three here might be pointing in the same direction. So you basically might have a residual flux. And if you have a residual flux on the curve itself, it really wouldn't start from zero. Because zero means B is zero and H is zero, which practically
That
means,
is why they say past history for.
yeah, past
So
magnetization.
the, I just say where the dipoles is all over the place. So you take a little bit before.
So the dipoles all over the place, but some of them will be or might be in the same direction. Remember, when you
Yeah.
have dipoles in the same direction, it will give you a residual flux. So all think about if it's millions of dipoles, right? And it means that at least a good bit of them probably in the same direction.
Yeah.
So if some of them in the same direction, we'll have something called a residual flux. Yeah, which means that if you try to magnetize that, the magnetization curve not going to start from zero. Somebody, okay, cool. Right. This, what I wanted to show you here. Well, this is a derived equation. You gotta know these. So this is just a read through, right? I'm gonna get to what I want to go through. This is eddy currents. Should I go through? Okay, oh, sorry, read through. So now non-magnetic material, the BH curve, that's straight line, we will adjust, right? However, for magnetic material, the BH curve is a non-linear line, right? And it follows the different paths for increasing and decreasing intensity. So for this first one here, it's starting from each one, which is 1 intensity. So to increase the intensity, you just change the value of I, right? Remember, I gives you H, and H gives you B. Remember, that is one of the first things you went through. So if you increase I, you could be increasing H, and if you increase H, you will increase B up to a saturation point. Cool? So in this point here, it's starting from each one, and it basically gonna go up to H2. And if you wanted the energy stored, it will basically just be the integral, which is just the area bounded here. Yeah, so this will be the area for the first one. So remember, we're going up in this one, right? Which means if it's going up, you're increasing the intensity. Yeah, so if you're increasing the intensity, the magnetic field will be storing energy. Yeah, because it's loading up, it's storing values, right? So that's what I mean by this here. So the difference from B1 to B2 of H dB will basically give you the energy. And that is for storing. The other way is when you're going down. So you're going from the high points back. And if you notice the energy here, or the area for this piece, it's actually smaller than this big area here. But if you subtract these two, you notice you will have a little piece remaining, because it's not the same, but if you subtract those two areas in green, you'll realize that you might have a little gray area remaining for the piece.
Yeah.
Right, that little area there is basically the energy lost. Also, but where
Oh,
that
that
energy
makes
going?
sense.
But where that energy going? Where the energy going is
Environment.
basically, yeah, but it have two type of losses. You have I squared R losses and you have hysteresis losses. And the two type of hysteresis losses, you know eddy currents.
Yeah.
The eddy currents is that type of loss. So you have eddy current losses and you basically have I squared R losses, right? So basically that we're going. So the hysteresis loop represents the losses in current one cycle, obviously. So remember the loop itself is this, right? So going up, coming back, then you have this part here, and then coming back around. It will never return to the initial starting point because it will maintain or retain some magnetization, right? So right, this loss of energy is dissipated as heat in the magnetic material and is the work done per unit volume in reorienting the magnetic moments of the material. So remember, the domain's initially all over the place, so you need to use energy to align it. Yeah? When you remove the magnetic field, some of it will go back to being all over the place. That energy there is heat, because you're literally moving something in a magnet. So you'll ever heat a spoon or something while you're cooking, and it get real hot. That heat is basically just the dipoles just real vibrating, and you can get heat, which is just the vibration of the dipoles. Cool. So that's basically doing the same thing. Explain how I went through just now. So this first piece you're increasing. So if you're increasing, all this will be the area. And then when you're going back down, when you're decreasing, which means you're decreasing the current, which means you're reducing the strength of the magnetic field, the area bounded will be just this piece on top here. So obviously you have
So
this,
the loss,
yeah, correct.
so the loss part could be due to the I square hysteresis, which is eddy
Hysteresis
currents.
losses. So the losses are due to hysteresis, not the drift. So this piece on top here is the area bounded when you're going back down, right? So that's the red piece there. But when you're going up from here up to here is the green piece. See now? So if you subtract the red from the green piece, you'll get this piece inside the curve right here. See now? And that area
Yeah.
there is where the hysteresis loss will be. So the energy released in the field during the decrease of the flux from B2 to B1 is less than the energy supplied to the field from B1 to B2, which is basically what is showing in there. And some of the field energy is lost. Where the energy go in, hysteresis losses, which are just eddy current losses. Cool. Just kind of going through it more, but the energy is being supplied to the core when the magnitude of the H is increasing, which makes sense, right? Because if you increase I, you increase in H, and if you increase in H, the energy supplied to the core will basically increase, right? So when you're moving away, which is when H increasing in both directions, this is not a negative H. This just means that the magnetic field strengthening in the opposite direction. So it's still H still increasing magnitude wise. The sign is still in the direction. Yeah. And then energy is released by the core when the magnitude of H is decreasing. Cool. When you're moving back to the origin. So the energy loss is basically just this here. Right, and history will represent the losses incurred in one cycle. As the frequency increases, the number of loss cycle increases. So remember, this loss here is for one cycle, right? If you had real cycles, the amount of losses you incur will increase because the losses is direct proportional to the frequency. Okay, if you have more cycles, you will have more total losses. That makes sense? So it's dependent on the frequency. Okay, right?
Yeah.
Cool. Right, so eddy currents is based just a lot. So read this. I don't go through this, but read it, and well, we'll go through this. So with the eddy currents, all eddy currents are just circulating currents in the material. Really all it is. And those circulating materials, well, circulating currents, if you look at this diagram, closer to the surface, the eddy currents are strongest. And as you keep going into the material, the eddy currents reduce. What this going to lead way to something called magnetic skin effect. Yeah? But anyway, so the induced EMF and the eddy currents increase with frequency, which makes sense, right? Okay, if you have more frequency, you have more losses. Cool. So to
So
summarize,
Lenz's law
go
would
ahead.
put it.
Where's that?
So Lenz's law work hand in hand with eddy current.
Yeah, because eddy current is something that's induced. And if you have something
Mm-hmm.
that being induced by something else, it will do in such a way to oppose the change that caused it. Yeah,
And Lenz's tell the direction of the EMF, the induced
circuit.
EMF.
Correct. Yeah, I really want to tell you. Well, you have your magnetic field effect. So take a read. And it basically telling you that the current will basically just bulk up and close to the surface of the material. And the inside of it will basically just be less. The density of it will basically be strongest at the surface and it'll be less dense in the center.
And this is from eddy currents.
Yeah. So eddy currents will basically tell you the circulating currents and the magnetic spin effect telling you those circulating currents will be strongest close to the surface.
Okay, that makes sense.
Yeah. Cool. Well, yeah, cool. Yeah, so lambda cubes. So you all came across these before?
Yeah.
Yes.
So this kind of, you're just going from a BH to lambda, right? So the first thing is to get the lambda, you basically just multiply b by the number of turns and the cross-sectional area, right? That's why let's go from b to lambda, right? And then to go from h to I, we know the equation for this. Ni is equal to HL. So you basically just make I the subject of the formula and you get HL and N, right? So you basically just multiplying the value of H by the length divided by the amount of turns, right? And I should just go from a BH to a lambda I and vice versa. Cool. But what this tells you is basically how the current changes with respect to the flux linkage. So if it keep increasing the current, the magnetic field will increase. Well, you can agree with that? If you increase the current, the strength in the
Yeah.
magnetic field will increase. But that magnetic field strength will have a maximum point. That maximum point will occur when all the domains point in the same direction. That is the maximum flux density you could get any material. So the material will just saturate. Yeah? So you could keep increasing the current past that point, it's not gonna give you any further increase in B. And if you convert it to linkage, remember linkage, if you think about it, right? Linkage is basically like how much flux lines cut in your coil. Yeah? So if I increase the strength of the intensity, and I will get more flux lines cut in my coil, that's the linkage. So if you increase I, you're increasing the strength of the magnetic field, which is just
So proportional.
correct. But the linkage now will also saturate because you will have a maximum linkage because when you core saturate, you're not gonna get any more flux lines. Cool. So
Yeah.
just remember the saturation point. Oh, just kind of summarizing everything. So the effect of the eddy current is to prevent a change in the flux density towards the center of the core, right? So the eddy current reduces the flux set up by the core, which is why there's a loss, right? And that widens the hysteresis loop. So if you have more eddy currents, the hysteresis will be wide. It'll be like a real thick. Yeah, because the losses is basically the area bounded by the curve. So if you have more losses, the actual area inside the thing will be thicker. So this area inside here, if you have more losses, this will just widen. It will get thicker. Yeah, which means you will have to give it more current to get the same shape. Yeah, well, I'm just kind of reducing the rest. Net effects reduction and the flux density B will reduce the density B. So that's kind of summarizing everything that we did.
That's why you want to use lambda I2 to see difference.
Yeah, so the both curves, the BH curve will give you how the intensity and the density changes. The lambda will tell you how the current and the flux linkage will change with respect to each other. It's the same curve, just a different representation of the variable. Good?
Yeah, because in vertical lifts is where I used to see the lambda I curve.
Yeah, you will use lambda because in a vertical lift, you care about current and you care about
Yeah.
flux linkage. Like those are the two most important things in vertical lift contactors. Yeah, cool. Now you see. Alright, so I'm gonna read that one. I ain't gonna stress about that one. Why is it? Okay. I don't want to push this. I can read that. Right, reducing eddy currents. Well, we have two main ways, right? So the eddy currents just give way to I squared R losses, which is just heat, right? So the two ways you could increase the resistivity of the core. Remember, it's circulating current, right? And if you have circulating currents, the best way to reduce current is by increasing the resistance, right? So in the material, it will be increasing the resistivity of the core. Cool? And the other way, which is the most popular way, is laminating the core. Yeah. So dividing the sections into smaller areas, each insulated from its neighbor. This results in smaller eddy currents flowing through the path. Remember, if you break up the path the current passing through, it wouldn't be able to form a loop. And if you break the loop, you're basically going to be breaking the current. And if you do all that, you're basically going to reduce the heating. Because you're literally breaking the looping, which is why laminating the cores does reduce eddy currents.
Kizar, I have a question.
Yeah,
How does it show up in a question by theory or through application?
theory. All this is theory. Majority of the course itself is theory, but Sanjay is a theory man. Like he will
Yeah.
ask you questions, but most of the time, yes, he will bring questions like calculations, but he will bring a lot of explain. Yeah.
And that's where the stuff now came in with eddy currents and how it linked to each other.
Mm-hmm. Yeah. So I can read the rest of this. It's just theory. What you need to pull from it, no, cause he didn't do any proofs, but it's just here for reference. Right, cool.
So ensure
So
you know your BH curve, your lambda I curve, and explaining.
yeah, make sure you know that. Because he could ask you to go from the BHD lambda to, which again is just knowing the equations. Alright, so cool. So I go into this one. So I'll kind of move slowly through this
One more
one.
question.
Yeah, go ahead. I can ask all the
So,
questions. Something
so
else?
when you explain them, you're going to start with the dipoles and your alignment and stuff.
For which, if they ask you for what, eddy currents or hysteresis?
For the BH curve or the lambda I.
Yeah, well,
I think you should probably give the definition of hysteresis first.
right, yeah, correct.
Then explain it.
Then you can draw the graph, and then you can show the
Explain
relationship
it.
between H and I and B and lambda.
Yeah, right.
So
That's
it
cool.
follows one path.
Mm-hmm.
Well, yeah.
I will start with a definition. Definition, and I'll graph to back it up. Equations good too, because you can kind of use the equation to get the definition, because it just explain how it does operate. Cool. Right. So, well, we kind of take a 3 minute breather, because I was talking a lot, and you come back
Yeah.
and start we go through the vertical lift. Right, I'm gonna pause the recording.